Okay, welcome to the fifth lecture of our reinforcement learning class, and in this video series we will talk about value function approximation. Okay, so where are we so far? We began with introducing Markov decision processes as a formal framework to actually formally define our decision-making problem. We defined optimal controllers through dynamic programming techniques, but afterwards also found out that in practice we usually do not have a model that we can use to estimate the value function. We then introduced Monte Carlo or time difference learning to actually estimate a value function given a certain policy pi, and in the upcoming videos actually derived a policy that optimizes actually the behavior of the agent through model-free interaction with the environment. We learned about Q-learning and SARSA as an off-policy and an on-policy variant to do control in model-free RL. And in this video series, we will be talking about a very practical problem that occurs if we actually want to solve such real-world problems that usually assume that the state space is actually far too large to actually do tabular Q-learning and to actually store all the available Q values into memory. And this will be what we are dealing with in this videos. Okay, so let's start with a little motivation before. One of the challenges that we are facing in real-world reinforcement learning problems is that the state space is usually very, very large, or it can be very, very large in practice. Here I have two examples. The first example is the backgammon example, which we'll also see in the lecture, where we actually can enumerate 10 to the power of 20 different states. And you can imagine if you want to do Q-learning on 10 to the power of 20 states, you actually need to actually store the value of each of the states over all the actions additionally, which actually is hardly being fittable into main memory of today's machine. And there's even more complicated problems, like for instance computer Go, where you actually can estimate the total number of states to be 10 to the power of 170, which is by far beyond everything that you can actually store. Okay, and to put on top of that, there's also problems that actually define continuous action spaces. So we now always dealt with discrete action spaces where we can actually enumerate the different states. But what is if we are doing a control problem that uses a continuous action space? Basically, maybe position not in a discrete manner, but in a continuous manner. And we have additional things such as velocity or angles, which we also have seen in the card ball example in the first lecture. So if we have continuous actions, also this is something like very, very similar to what we have seen in backgammon and computer Go. We have a large number of different states that are actually available in the environment. Yeah, and the problem with large MDPs is simply there's too many states and actions to store them in memory, and this is one of the side of the coin. And the other side of the coin is that it is usually far too slow to actually learn the value of each state individually. So you have seen that we're bootstrapping actually the values, and this requires also several passes over these states. And in tabular Q-learning approaches or tabular SARSA, we would actually have eventually to visit each of the states several times to actually converge to the real Q value, which can be very exhausting in practical applications. So hence we can no longer build the table, and hence we need other approaches to do so. There's also another challenge actually that's kind of related to the problem or the challenge of generalization. Actually, we want to generalize across states, and actually we want to take benefits out of the similarity between states. So let's assume that we are actually training an agent that plays Pac-Man, and let's say we have through experience and through interaction with the environment, we have discovered that this state is somehow a bad situation. If you know Pac-Man, you actually need to eat all the small little dots, and you need at the same time avoid the ghosts. And actually, you're in the tunnel, and believe me, this is a very bad situation. So if you actually do naive Q-learning, you in principle have no knowledge about the state. So for Q-learning or for tabular Q-learning, also depending on how you describe your state, but if you define a Markov state, you have actually no idea how good you are doing in this state. However, as a human, you would say, this is actually very similar to this situation, because actually, yeah, there is a tunnel and you're somehow trapped by the ghosts. So actually, but if you're doing tabular Q-learning, I mean, the states are different and you have no idea actually how good the state is. Or if you know that the state is bad, actually, you also have no idea how good this state is. So this state is actually mostly the same as the first state. However, there is a dot missing in here. And actually this makes it a different state. And you have no way of actually generalizing across different states and to actually estimate a Q value from the available knowledge. And as the name of the lecture suggests, what we want to do is we want to approximate the value function. What we've did so far, we represented the value function in an exact way, meaning that we actually hold a table that holds a distinct value for each of the cases. So we have for a value, if you want to estimate the state values, we actually have one entry per state, and if we want to estimate the Q values, we have one entry per SA pair. And if we now approximate it, what we actually want to do is we want to approximate V or Q using a function approximator, which is something that we usually do in machine learning a lot. And we can do this, for instance, with neural networks, with polynomials, or radial basis function, or whatever comes to your mind. What we will do in this lecture, we will focus on differentiable approximators, because then we also know a gradient, and then this actually plugs in very nicely in our definition of the small updates we also derived in the value function estimation problems in the last two lectures. However, always see that actually our problem is a little bit different from classical supervised learning, as we actually derive our targets by our by our function approximator itself, and this is one of the problems that we will actually deal with in this lecture. So if we want to actually find a function approximator that approximates V or Q with some parameters V, there is different ways of actually designing such a function approximator. For instance, what we could do is actually we could define a function approximator that takes S as input and with a set of parameters V outputs our value estimate of this state under the parameters V. W. What we could also do is, if we want to approximate the Q function. So what you would naively assume is, we just define a function approximator that takes as input S and A, so state and actions, and through a set of learnable parameters W outputs the Q value of this state action pair. Another way, or actually a really nice way to actually reduce the problems that of actually fitting a function that actually minimizes the error on this, is to take knowledge about the action space. So actually, if you could enumerate the actions in your system, so actually if we deal with discrete actions, we can also come up with a slightly different architecture, which we will also see throughout the next videos, where we actually can also approximate the Q function giving a single input state S, and through a parameter set having several regression heads to actually estimate the certain Q values of several actions or all the available actions given in a certain state S. Yeah, so what's actually the benefits we can actually do this? If we do it something like this, there is no need actually to actually store the whole table anymore. We can just store the parameters W. And this is usually much less than the actual parameters itself. However, as we have seen, we have problems introduced by bootstrapping and all these non-stationarity and off-policy, on-policy learning. There's a lot of convergence properties that we are actually have guaranteed under TD learning and tabular Q, also TD learning and Q learning in their tabular representations, they actually do not longer hold for approximated versions of them. We will see a little bit of that in the next lesson. Just to give you one more motivation, so actually the basic idea to actually solve the incoming problem of Pac-Man, what we first need to do is actually to define, or the general idea is actually giving on some your state information to actually derive a number of features. In this example, you could run some image processing on it, or you actually get some internals of the simulator, and then you would define a state as a number of features. Maybe you derive the distance to the closest ghost, or the distances to the closest dots, or the number of ghosts, or you can also derive features such as is Pac-Man in a tunnel, which could be a binary features. And given such a feature representation where you actually have to still maintain the Markov property of the state, so you need to really fully describe the state. But if you have such a feature representation, actually you can use this to do either tabular Q learning or functional approximation approaches, which we will do in this lesson. I told you very shortly that we will focus on differentiable function approximators in this lecture. And as we know, in general, machine learning is really keen on doing gradient-based approaches to actually optimize a value function. And the general idea is to say we define a cost function, and our cost function is something like the Q value of our, or the target of our, the Q target of our state action pair, so actually the sample minus actually the prediction of our network. And what we can do is, if we do this like this, and we do a linear value function approximation, we will do in the next step, we just derive a number of, this is nothing else than actually a representation of the state multiplied by some parameters v. So actually it's a linear function approximation, linear in the parameters, but possibly non-linear in the features, which actually make them also very powerful in practice. And if we want to optimize this, we can just take the derivative of this cost function as we usually do it in stochastic gradient descent. And if we derive it with respect to our parameters w, we actually come up with this derivative. And based on this derivative, we can also, like in a gradient descent way, update our cost function or update our parameters such that our cost function gets closer to the actual target, which we could do like this. And the only thing that we need to now care about is how to define this Q target. And this Q target is simply depending on what we're actually doing. So if you're doing like Q learning with linear value function approximation, it's just our one-step reward plus max operator on the Q target. This is just output. We put this in here, and we can just run the optimization. We can also do this with Sarsa as well, and we can also put in the sample return, and we can use Monte Carlo to actually bring our parameters W close to the real targets that we actually want to predict. So actually what we will be doing in here, we will actually still sticking on to our generalized policy improvement, generalized policy iteration framework where we initially did the iterative policy evaluation step in here, and we will just do an approximate policy evaluation step where we learn parameters vectors W in order to actually find a function approximator that approximates the value function.